Hi, Nicole. To find the molecular formula here, first you need to find the empirical formula. You have done so, but then you have also requested a complete explanation of all the steps, and so here we go. This compound has carbon, hydrogen, and oxygen in it. I can easily find the amount of carbon in there because it produced this much carbon dioxide. I don't care about the dioxide, I just care about the carbon. The reason why I don't care about the dioxide is because this was burned in oxygen. That means that the burning process used up oxygen not only from the compound but also from the air. So I have no way of knowing how much of this oxygen came from the compound and how much came from the air. So I only care about the carbon here. Let's get that carbon. Let's get how many moles of carbon that is. So this is 2.868 grams of carbon dioxide and 44.01 grams of carbon dioxide are in 1 mole of carbon dioxide. I get that from the periodic table by adding the molar mass, or the atomic mass of carbon, and the atomic mass of oxygen times 2. That gives me 44.01 grams per mole. Now, is that what I want? Not exactly, although numerically it is. In 1 mole of carbon dioxide, there's 1 mole of carbon. That's what I want. So the moles of carbon dioxide cancel, the grams of carbon dioxide cancel, so I end up with, just like on a cooking show, I have done this calculation for you in advance, 0.06517. You have also done this calculation, so no mystery here. So this is how many moles of carbon are in the molecule. So in the empirical formula, the empirical formula is going to go CHO something. The C is 0.06517. Can't have a decimal as a subscript in a molecular or empirical formula, so we're going to be dividing this number by some other number or by itself to get whole numbers here. So more on that later. And now let me go for the hydrogens. Now let me just get rid of this. Now the hydrogens are given by the water. Notice there are 2 hydrogens for every 1 water molecule. That's going to make a difference. So 1.567 grams of water. Using the periodic table, I add up the atomic masses to get 18 grams of water in 1 mole of water. It's very important to respect the significant figures here when you do empirical formulas. And in every 1 mole of water, this is an important step here, there are 2 moles of hydrogen, not 1 mole of hydrogen. So these all cancel out. I end up with moles of hydrogen, which is what I wanted. And the moles of hydrogen are 0.1739. So that's 0.1739 moles of hydrogen. So far, our empirical formula looks like this. Alright, all we need to do is find the O and then divide all these by something to get them into whole numbers. Alright, so let's go get that O. How can we get the O? Remember, this was burned in oxygen, so I have no way of knowing how much oxygen was used from the air. So how do I know how much O there is in this compound? No problem. The way to know that is by subtracting out the carbon and subtracting out the hydrogen from the initial mass. Remember that the initial mass was 2 grams. If the thing only has carbon, hydrogen, and oxygen, if we take out the carbon and take out the hydrogen by subtraction, we can get the number of grams of oxygen there are. Now, of course, I cannot subtract moles of carbon from 2 grams. I must convert these moles of carbon back into grams of carbon. It's not 2.868 because that was carbon dioxide. It's not 44.01 because that was carbon dioxide. I gotta convert this to grams of carbon. And you did that, but you rolled it into one step with something else. Let me just do that for you again over here as its own step, just to be nice and clear. In 1 mole of carbon, on the periodic table, there are 12.01 grams of carbon. So 12.01 grams times 0.06517 moles, and that's 0.7827. That's 0.7827 grams of carbon. do the same thing for hydrogen. I'll do the same thing for hydrogen here. I got 0.1739 moles of hydrogen, and in 1 mole of hydrogen, I have 1.008 grams of hydrogen on the periodic table, and so I end up with, I mean, this is like 1 times 0.1739, so I end up with 0.1739. Let's just make sure. 0.1739 times 1.008. Oh, I'm sorry, it's 0.1753. Okay, my bad. 0.1753, and that's grams of hydrogen. So I will take those grams of hydrogen and subtract them from 2 grams. I will take those grams of carbon and subtract them from 2 grams. And you've done that down here. You've said 2 grams minus, remember, these are the grams of carbon, and these are the grams of, and these are your grams of hydrogen, and you got 1.042 grams of oxygen. So, to save some time here, let me just take this directly in your page, grams of oxygen, and convert this to moles of oxygen. Now, on the periodic table, there are 15.9994, I'm sorry, that's wrong. In the periodic table, in 1 mole of oxygen, there are 15.9994 grams of oxygen, or 16.00, depending on how your periodic table looks. And so you get 1.042 divided by 15.994. You get 0.06513. You get 0.06513 moles of oxygen. Okay, so that's oxygen. So far we have the empirical formula of 0.0, what was it that we had? 0.06517, 0.1739, 0.06517, and 0.1739, and O is 0.06513. 0.06513. Okay, this is the empirical formula. Now, the rule for empirical formula is you must divide all of these by the lowest of them. Who is the lowest of them? Oh, I think it's you, right here. I will divide all of them by that. Divide 0.06513. Divide 0.06513. Divide 0.06513. Okay? So I get C1. That's great. Ooh, this is not great. I get H2.66, and I get O1. All right, so this 2.66 can't just stay here. We need to do something about that. Now, the other rule for empirical formulas is if you have some decimal here, even after you've divided by the lowest, you must multiply everything by a number that will change this decimal into a whole number, or within 0.01 of a whole number. You know, it has to be very, very close to a whole number. So let me buy some room over here. Get me some room here, please. Okay, great. Now, back to the pencil. Okay, so here, this 2.66. What is 2.66? Well, 2.66. Ah, yes, 2.66 is 2 2/3, because 2/3 is 0.6666666. Now, what is that as an improper fraction? Well, 2 times 3 is 6, plus 2 is 8. There's the 8. I keep the same denominator, so it's 8 over 3. So what I've got here is C1 H. So what I've got here is C1 H 8/3 O1. Obviously, I can multiply them all by 3 and get whole numbers. So if I multiply them all by 3, I get C3 H8, because 3 and the 3 cancel, O3. C3 H8 O3. That is the correct empirical formula. Now, Nicole, here's where your mistake came in. Down here, you see, down here, you have, right here, you divided 0.1753 grams of hydrogen by the molar mass of hydrogen, but you put the molar mass of 2 hydrogens, not 1 hydrogen. That's why you had a 1.33 here instead of a 2.66 there. That's why you had C3H4O3 instead of C3H8O3. And that's going to be very important. Why? Because we don't want the empirical formula, we want the molecular formula, all right? So let's find the molecular formula. Now, real quick, the molecular formula is found like so. They have given you a freezing point depression of negative 0.0894. They dissolved the compound in water, and the freezing point of water went down from 0 degrees Celsius to this temperature. This is known as freezing point depression, given by this symbol. And freezing point depression is governed by this math formula. A constant for water, it is 1.86 times the molality, which is moles of solute over kilograms of solvent. In this case, the solvent is water, times the particularity. I use I, your textbook might use N, and that's just how many particles each molecule breaks up into. If it's an ionic compound, it could be 2 or 3. For example, for NaCl, there are 2 ions, so the particularity is 2. But in this case, with a carbon, hydrogen, oxygen compound, that's molecular because it's got no metals. They're all nonmetals. So if it's molecular, the particularity is always 1. One molecule of a molecular compound is going to dissolve into 1 molecule at a time. So let me just substitute the numbers in here that we know. The constant for freezing point depression when water is involved is this number in units of degrees Celsius per molal, and molal is moles over kilograms. So the molality, this M here, is the moles of the compound divided by kilograms of water. And now in this case it was 25.0 grams of water. Move that decimal point to the left 3 times, 1, 2, 3, you got 0.0250. 0.0250 kilograms of water. Okay, now the particularity is just 1, so this I was 1 because it's molecular, not ionic. Now what about these moles? How do you find these moles? Well, let's see. Let me just leave that blank for right now. 0.0250 kilograms times 1. Okay, that looks like a 2 times 1. All right. Now, the moles. How do you find the moles? Well, 0.1107 grams of the compound were dissolved. All right. So let me write that down. 0.1107 grams. Now, to find the moles, of course, I have to know the molar mass, right? In 1 mole of the compound, there are some grams of the compound. The grams cancel, and you get moles. So that's the moles. This whole thing right here is the moles. Notice I have used X for the grams because I don't know the molar mass of the compound. That's what I want to know. Notice that this is the only unknown thing. There's only one unknown thing. That's my X. Everything else is numbers. So I can change this into an algebra equation and just solve for X. Here, let me just take out the units to be just a little clearer. Divided by X, all right, times 1. I can just leave off the 1 because anything times 1 is just itself. All right, so now I can just solve this equation for X. Okay. Whoops. Sorry, that's my phone ringing, but I'm going to ignore that because you're more important right now. Okay. So, sorry if that's distracting. I'm going to rewrite this equation now. Notice that 0.1107 is divided by X, and this is also 0.1107 is also divided by 0.0250. So I can put this X down here. So this is going to be negative 0.0894 equals negative 1.86 times 0.1107 divided by 0.0250x. Now I can just multiply both sides by x to get x out of the bottom. So, here, let me just, alright, now we don't have to be bothered by that. So, 0.0894 times x equals 1.86, that's negative 0.1107 over 0.0250. All right. And now I'm going to divide both sides by this number to get x alone, of course. So 1.86 times 0.1107 divided by 0.0250, also divided by negative 0.0894. Okay, now I can just solve for x using the calculator. 1.86 times 0.1107 divided by 0.025 divided by 0.0894. Of course, a negative divided by a negative is a positive, so the answer is 92.1. Right? And that is in grams per mole. Okay, so that is in grams per mole, 92.1 grams per mole. So that is the molar mass of the compound. And why is that useful? It's useful because this is the empirical formula, and it is going to have a certain formula mass. If the molar mass is the same as that formula mass, then the molecular formula is easy. But if the molar mass is different, then you have to multiply this whole thing by another number. Let me show you exactly what I mean. Now, I'm going to take the formula mass and divide it under the molar mass. So the formula mass divided by the molar mass. It's gonna give me some number. All right. So the molar mass was 92.1, and the formula mass is whatever it is. And if I get 1, then the empirical formula is the molecular formula. But if I get 2, then I'm going to have to multiply all of these by 2. So it's the molecular formula is going to be C6H16O6. If I get 3, I'm going to multiply all these by 3. It's going to be C9H24O9. Okay? Let's see what I actually get. Now, what do I mean by formula mass? I mean these added up on the periodic table. So, the formula mass is going to be 3 times carbon, which is 12 on the periodic table, plus 8 times hydrogen, which is 1.008 on the periodic table, plus 3 times oxygen, which is 15.9994 on the periodic table. You add those all up, and what do you get? Haha, that's right. You get about 92. So 92 divided by 92 is about 1. So the molecular formula is the same as the empirical formula. It is C3H8O3, and that is all. Thank you, Nicole.